Okay, everybody, let's talk about the key idea of this lesson, which is logical equivalence. Logical equivalence is just sort of our fancy word in logic for saying when two statements mean the same thing or when they are equal to each other. So when you deal with the world of numbers, we talk about things being equal. Two numbers are the same if they're the same number. When you deal with the world of logic, then the objects we're working with are not numbers, they're statements. And we say two statements are equal if they have the same meaning. Or another way to say it is two statements are equal if their truth tables line up exactly, match exactly. If the truth values match up line for line in the truth table. In symbols, we express this using the equal sign. So if we haven't previously said that one statement in logic is equal to another statement, we now will say that when those two statements are logically equivalent. And logically equivalent, the definition says to look at the truth tables. They have to be true in the same circumstances and false in the same circumstances. And the way that we express it is by putting an equal sign in between them. So I want to talk again about the biconditional. So let's ask a question. Is that biconditional P if and only if Q, is that logically equivalent to saying that both P and Q are true or both of them are false? I'm going to write it in English first. P and Q are both true, or P and Q are both false. So we made this observation by looking at the truth table that this thing is true exactly when either P and Q are both true or when they are both false. And what I want to do now is see if that really is a right interpretation. So this expression, P if and only if Q, we're going to see if it is equivalent to this. And what I want to do now is just first express this English language expression in logical symbols. So P and Q are both true is just a matter of saying P and Q. Because we know for the conjunction, the and is exactly how we say both of the things are true. The conjunction in particular is only true when both P and Q are true. So that's like expressing the first part of this, P and Q are both true. And then the other part is P and Q are both false. To say they're both false, we need to have not P, that means P is false, and also not Q, that means Q is false. So this one says P and Q are both false. This one says P and Q are both true. And if you look at this statement we're trying to untangle here, P and Q are both true or P and Q are both false. So the thing to put in the middle here, the symbol to put in there, has got to be the or the disjunction that's called. So we want to know, is P if and only if Q, is that equivalent to this P and Q, or not P and not Q. So this is our statement. This is example number 3 in the lesson. And we're going to answer this statement now by using a truth table. If we want to know if two things are logically equivalent, the way that we establish it for now is by using the definition. Definition says if their truth values match up line for line in a truth table. So all we need to do is produce a truth table of this, P if and only if Q, and a truth table for this sort of longer looking statement, P and Q, or not P and not Q. And then we're going to see whether the truth tables line up, whether they match. So let's go ahead and do it. The way we're going to do this is by doing first our initial variables, the P and the Q. We're going to have one column for P if and only if Q. That's like one expression that we're looking at. And then we're going to have another column with this expression. So here we're going to have P and Q, or not P and not Q. All right, and what we have to do now is just fill in this truth table. So let's go ahead and do it. First of all, under the P and the Q, we put our usual every possible combination of true and false. False, they can either both be true. The first can be true and the second one false. The first can be false and the second one true, or they can both be false. So we have 4 rows again, and that's because we have 2 variables to deal with. Now, P if and only if Q, for this one, we can just look at the truth table that we made above and copy it down. It was the one that looked like this, and it went true, false, false, true, and I had these guys set up in the same order, so I'm just going to copy this one down. The P if and only if Q goes in here. It's true, false, false, true. Okay. Now we want to deal with this one, and this one is a little more complicated because it is not just a simple logical statement, it's a compound statement. It has this piece in parentheses, this piece in parentheses, and then the disjunction. So here's how I'm going to do it. I'll choose a different color and maybe a slightly smaller pencil size to fill in the values along the way, and then when we get to the final bit, we will we'll fill in the final value, the truth value for this entire thing. We'll do it back in purple again. So let's start with the P and Q. Now, if P and Q are both true, here, true and true, then the value of P and Q is going to be true. So we're going to put in a little T here. Let me see, just moving straight down, if P is true and Q is false, then the value of P and Q is false. If P is false and Q is true, then the value of P and Q is false. Because for the and, for the conjunction, the only way it gets true is if both of them are true. And then finally, if P is false and Q is false, then we still get false. The only answer here that we get that's true for P and Q is when they're both true. Now let's try not P and not Q. This one, I'm just going to go down quickly and fill in not P right here. And remember, here's P. So for each one of these, not P is just going to be the opposite. So what if P is true, then not P is false. If P is true, then not P is false. If P is false, then not P is true. And if P is false, then not P is true. So this I obtained just by looking at the column for P and then taking the negation, switching it. Now I'm going to do the same thing under here for the negation of Q. I'm going to fill those guys in. They're just going to be the opposite of the Q. So on the top row, Q is true, so not Q will be false. The next one, Q is false, so not Q is true. The next one, Q is true, so not Q is false. And the final one, Q is false, so not Q is true. What I'm going to do now is take the conjunction of not P and not Q. So when the not P is represented here, the not Q is represented here, and the conjunction of those two, I know that the conjunction is going to come out true only when both sides are true. And we don't have true here, here, or here, but we do have it down here, which means I can quickly fill in. This is for this conjunction between not P and not Q. That one is false, that one is false, that one is false, and the last one is true. Okay. These are the truth values for this parentheses here, the not P and not Q altogether. These are the truth values for the parentheses here. And now what I want to do is combine the values for these parentheses and the values for these parentheses. You have to focus. It's this sort of middle column that goes false, 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 true, that we're comparing with this column, true, false, 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 and we're combining them together with an or a disjunction. So remember, for the or, it comes out true when either one of them or both of them are true. So when we compare, this is the P and Q, and then or, not P and not Q, true or false, one of those things is true, so that comes out to be true. And this one I'm going to put in purple, because this is actually the value of the whole expression. Since one was true and the other was false, we're going to come out to be true there. In the next case, we have false and false, which means this one comes out false. In the next case, we have false and false, so this one comes out false. And in the final case, we have false and true, so this one comes out to be true. Now, we want to return. So first of all, this is our truth table here for the expression P and Q, or not P and not Q. And this is P if and only if Q. And the question is this logically equivalent to this? And that's just a matter of, do the truth tables match here and here? You'll see that the first line, they're both true. The second line, they're both false. The third line, they're both false. And the fourth line, they're both true. It means on every single line, their values match each other. They don't disagree anywhere. And because of that, we would answer here, yes, they are logically equivalent. And why? It's because the truth tables are identical for those two expressions. And in particular, what I'm talking about is that truth table and that truth table come out exactly the same. Okay. That's an example of how we show the logical equivalence of two expressions. The final conclusion, or the final thing that I just want to make a note of, this is just a notation question. Because these are logically equivalent, then in the world of logic, we say that we write that they are equal. So we have, now here's our conclusion. Our conclusion is that the statement P, if and only if Q, is equal to, I think this is the first time we've used the equal sign with logical symbols running around, this is P and Q, or not P and not Q. Another way to look at this equality is the following. Think of this expression as just being the same, meaning the same thing as this expression. And if you were in a proof, for example, and at one point you had arrived at this expression somehow, if you wanted, if it would help you, you could replace this with this other form of the same statement, because these two statements mean the same thing with regards to P and Q. So this is just like when you learn things like trig identities, or when you learn things like factoring, two ways of presenting an expression that mean the same thing at their heart. They're equal to each other. So the same thing is true in logic. And one of the ways that we'll use them is by sometimes replacing what we see on this side with what we see over here, and sometimes going the other direction. All right, that's it. We'll come up with one final video talking a bit about the contrapositive, and then that'll be it for today. Thanks.